When you think about really complex engineering challenges, a cement mixer probably isn't the first thing that comes to mind, but it absolutely should be. Today, we're going to do a deep dive into the incredible systems engineering required to transform one of construction's loudest, dirtiest workhorses into a silent, hyper-efficient, and truly intelligent machine. So here's our blueprint for this explainer. We'll start with a fundamental problem we're trying to solve, then walk through the elegant hybrid architecture. We'll get into the weeds on motor selection and software control, cover the non-negotiable topic of safety, and then look ahead to what this all means for the future of heavy equipment. Okay, first things first, to really appreciate why the new hybrid solution is such a game changer, you have to get a solid grasp of the fundamental problem we're trying to solve. You have to understand the core inefficiency built into every traditional diesel mixer on the road today. So here's the big insight, the thing that might surprise you. The single biggest problem with a concrete mixer has almost nothing to do with driving down the road. It's all about what happens when it gets to the job site and just stops moving. Now, check this out. This chart tells a pretty shocking story. That massive diesel engine, it spends about half of its entire workday not driving, not working hard, but just idling. Just sitting there, burning fuel, making a ton of noise. For what? Just to keep that drum spinning out a crawl. From a systems engineering standpoint, this is just wildly inefficient. Think about it. You're using a 300 kilowatt engine to do a job that only needs about 30 kilowatts. It's massive overkill. And that leads to a whole cascade of problems, noise, emissions. But here's the real kicker. For the final product, the drum's speed is physically tied to the engine's RPM. That means inconsistent mixing, which is a huge risk to concrete quality. All right, so that's the problem. Now let's talk about the solution, which is where the engineering gets really elegant. We're looking at what's called a P2 hybrid plus ePTO architecture. That ePTO stands for electric power takeoff, and it changes everything. The absolute key concept here, if you remember one thing, remember this, is decoupling. We are functionally and physically separating the job of moving the truck from the job of spinning the drum. This means the big diesel engine can shut off completely at the job site. Total silence, zero on-site emissions. The entire mixing operation is taken over by a dedicated electric motor running off a high-voltage battery. And this just lays it out side by side. The contrast is stark, right? Every single weakness of the old system, the inefficiency, the noise, the lack of precise control, becomes a major strength with the ePTO. This isn't just an incremental improvement. It's a complete paradigm shift in how these machines work. Okay, let's drill down into the heart of this ePTO system, the motor. Now, you might think you just find a big electric motor and bolt it on, but it is so much more complicated than that. And the reason why is the unique physics of concrete itself. See, concrete is what we call a non-Newtonian fluid. That basically means its thickness, its viscosity, changes under stress. After it's been sitting for even a few minutes, it settles and thickens up. So that initial movement, what we call breakaway, is an extreme engineering event. The milkshake analogy is perfect. It takes a massive amount of initial force to get it moving, and we can put a number on that force. We're talking about more than 800 Newton meters of peak torque. That is a huge amount of twisting force, and it's needed for just a few seconds to get that settled load moving. This single requirement, that 800 plus Newton meters, drives the entire design of the motor, the inverter, and even the battery system. It is the system's critical design driver. But you can't just pick a motor that hits that peak torque number. The real art is engineering for efficiency across the whole duty cycle. You start by analyzing all the jobs the motor has to do. Then, using advanced tools like finite element analysis, you literally design an island of super high efficiency. We're talking over 96% into the motor's performance map. The final critical step is to make sure the most common task, that slow agitation during transport, lands right in the middle of that sweet spot. That's how you squeeze every last minute out of the battery. So we've got the muscle, a powerful and incredibly efficient motor. But of course, muscle is nothing without a brain. And in this system, the brain is all about software and the seamless digital conversation happening between the main controllers. The system architecture is a two-tiered command structure. You have the SCU, the supervisory control unit, which acts as the foreman. It sees the big picture and makes the strategic calls like, okay, we need to mix it 2 RPM. Then you have the MCU, the motor control unit. This is your specialist. It takes that high-level command from the foreman and executes the complex physics of spinning the motor with incredible precision. And they communicate over a standard vehicle network called J1939. You can see it here. It's a constant digital handshake. The SCU sends a command, set motor speed to 200 RPM, and the MCU is constantly reporting back its status. Okay, I'm currently using 45% of my torque. And, by the way, my winding temperature is now 110 degrees Celsius. This constant conversation is what allows the entire system to work together safely and efficiently. Now let's talk about something absolutely critical in this world: reliability. A sudden shutdown on a construction site isn't just an inconvenience, it's a disaster. You can lose an entire truckload of concrete. So the design philosophy isn't to build a system that never fails. That's impossible. The goal is to build a system that fails gracefully. And a key strategy for this is called torque derating. It's a really elegant safety feature. Instead of the system running at 100% until it hits a thermal limit and then just shutting off completely, bam, the controller is much smarter. As it senses it's approaching a limit, it proactively and smoothly reduces the available power, giving the operator an alert and enough capability to safely finish the job. And you can see that strategy in action right here. At a normal operating temp, you have 100% of your torque. But as the motor heats up, say to 130 degrees Celsius, the controller automatically pulls the available torque back to 75%. If things get really critical, it enters a limp mode with maybe just 10% power, enough to keep the drum turning, but protecting the very expensive hardware from destroying itself. And this is all part of a much bigger picture called functional safety, governed by strict automotive standards like ISO 26262. Think about it. A mixer accidentally reversing and discharging on the highway? That's a catastrophic hazard. So the software has a simple, bulletproof rule. If the vehicle speed is over 10 kilometers per hour, any command to reverse the drum is blocked. Period. Or high voltage safety in a crash. The system actually uses the motor itself to safely discharge the dangerous high voltage capacitors in less than 5 seconds. So, when you put all of these pieces together, what does it all mean for the future? Well, it's much bigger than just making one truck quieter and cleaner. It's about fundamentally transforming these machines from dumb tools into intelligent data-gathering platforms. And here is the most profound shift of all. The motor is no longer just a motor. It becomes a sensor. Because the controller is measuring torque with such incredible precision, millisecond by millisecond, it can detect tiny fluctuations in the load. What does that mean? It means the system can actually feel the consistency, the slump of the concrete inside the drum in real time. And that capability unlocks the entire next generation of tech. We're talking about using advanced silicon carbide electronics to boost efficiency by another 5 to 8%. We're talking about adaptive control, where the truck automatically adjusts its own mixing speed based on that real-time slump data. And the real holy grail, V2X diagnostics, using telematics to stream all that data to the cloud, allowing algorithms to predict a failure before it ever strands a driver on a job site. So you see, this engineering blueprint we've walked through, decoupling the work from the engine, precision motor control, intelligent software, and layered safety systems, this isn't just for cement mixers. It's a proven architecture for electrifying the entire world of heavy-duty machinery. The question is no longer if we can do this. The only question now is, what giant gets electrified next?